All right. So today we're going to start doing path integrals for fermions. So we'll discuss Gaussian integration, and then we'll apply it to define the weak theorem and find the final rules for fermions. Okay, so let's start with Gaussian integration. First, let's consider the real case, so real integration. Even though, as I said, in principle we'll think about the complex integration. Psi and psi bar are independent, but just to warm things up. Since we're interested in fermions, as we said, we'll consider a Grassmann algebra over real numbers. So real integration means over real numbers. Okay, Grassmann algebra, I remind you, means that besides the normal numbers, which are called even members of the algebra, we also have the odd members, which are anti-commuting objects. But the algebra is over real numbers, hence real integration. So, we'll write this as a theorem. So we'll consider a real n by n antisymmetric matrix A, such that A squared has negative non-zero eigenvalues. Negative is because it's an antisymmetric matrix. So if it has real eigenvalues, it's supposed to be non-zero, but non-negative also, non-zero also, meaning that there are no, the matrix is not singular, right? So the matrix is antisymmetric, and if it has negative non-zero eigenvalues, it also means that n is actually an even number. And for x1 up to xn Grassmann numbers, Grassmann variables, we have the formula transpose dot a dot x. So that's our Gaussian integration that we want to do. And this is 2 to the n square root determinant a. Okay. I remind you that for integration of usual real numbers, not Grassmann algebra, we get 1 over square root determinant, right? So these come in opposite ways, and again, what's the result of this is that you have a supersymmetric theory with both the same number of degrees of freedom and the same matrix. Then you would get a square root determinant from the fermions and 1 over square root determinant from the bosons, which would cancel. So easy to remember, they're opposite. Well, there's a 2 to the n, but as you know, constants in path integrals are not interesting for us. All right, so let's prove that. So we consider first n equal to 1, sorry, n equal to 1, that is n equal to 2. The simplest case, right? And then, in this simplest case, real antisymmetric matrix with non-zero eigenvalues means this. I mean, antisymmetric already means this. The diagonal can only have zeros, right? Because it's antisymmetric. And then this is lambda minus lambda, and non-zero eigenvalue means lambda is different than 0. And then a squared is, of course, you know, this times this is minus lambda squared, the same this times this. So we see the condition that indeed this is now even diagonal. So the condition was that a squared has negative non-zero eigenvalues. So if lambda is different than 0, this is true. Right? Determinant A is lambda to the 4th positive. Right? And
determinant of A squared.
Sorry, this one of A squared. Thank you. Yeah. And then determinant of A is lambda squared. And then we want to write this thing. So x transpose dot A dot x. If x is x1, x2 vector, then you get x1, x2 here, x1, x2 here, right? So here we get lambda x2 and minus lambda x1 multiplied with x1, x2. So this is lambda times x1, x2, and then minus x2, x1. But these are Grassmann numbers, so they anticommute. So this is 2 lambda x1, x2. Right? All right, so then how about the exponential? E to the x transpose A dot x. Well, exponential means sum of one over x to the n over n factorial, right? But I remind you that for Grassmann numbers, xi squared is 0, right? And this exponent already has both x1 and x2, right? And so by, okay, x1 and x2 anticommute. So by considering any power higher than 1 in this exponential, I will always get an x1 squared or x2 squared. So that's all 0. So the only thing non-zero is the 0th order and the 1st order, right? That's 1 plus xt x, that is 1 plus 2 lambda x1, x2, right? And now let's do the integral of this. So integral dnx, now it's integral dx1, dx2, right? Of this thing is integral dx1, dx2, 1 plus 2 lambda x1, x2, right? I remind you, for Grassmann numbers, integral is the same as differentiation, so integral of 1 gives 0, right? And then integral dx1, x1 gives 1, integral dx2, x2 gives 2, but we have to remember the sign. So, well, there's a 2 lambda here. And then, I suppose I should have said, so we have to choose a specific order in dnx. I mean, the natural order is dx1, dx2, but it's actually a choice of ours, and I choose to have dx2, dx1.
Is it really arbitrary because differentiation choices, different signs. Yeah.
Different signs, yes, but I mean that's really our. You know, you have to define what this thing means. I haven't said to you what this thing means. I have said to you that what this thing means, but I haven't said to you what integral dnx means. Right? So this is a choice that amounts to a choice of sign. Right? So for bosonic variables, it's obvious. It's just a product, and the order doesn't matter. But for fermionic variables, the order matters. So the definition of integral dnx amounts to the definition of the order of the various components. And I want to choose this. And then in here I have 2 lambda. Then integral dx1 x1 gives 1. Integral dx2 x2 gives 1 as well. So this is just 2 lambda. Okay? And determinant A, as I said, is lambda squared. So that means square root determinant A is lambda. Okay, so this is 2 square root determinant A, which is exactly this formula for n equal to 1. Okay, so for n equal to 1, I've proven it. Now, to prove it in a general case, it's enough to prove that the general case reduces to n times the n equal to 1 case, right? So, in other words, it's enough to prove a version of the Jordan lemma for antisymmetric matrices in the Grassmann case, right? So let's say Jordan lemma for antisymmetric matrices in the Grassmann case. Okay. So what is the Jordan lemma? That there is a matrix B that acts on the space, so a change of basis. So for a symmetric matrix, I can, the equivalent of the lemma in question would be that there is a transformation on the basis that diagonalizes the matrix. For an antisymmetric matrix, the Jordan lemma says it can be brought to block diagonal form where the blocks are these, with lambdas being the equivalent of eigenvalues. So there is a matrix B, which is a change of variables such that the transformed matrix, which is B transpose A B, has a block diagonal or Jordan form. Right? So that is to say BTAB is 0 lambda 1 minus lambda 1 0, one block, and 0 lambda 2 minus lambda 2 0, another block, so on until 0 lambda n minus lambda n 0, and the rest is zeros, right? Okay. And then in this form, we note that determinant of A, B being an SO to M matrix, that is to say B minus 1 equal to B transposed, right? So then determinant A is the same as determinant B transpose AB. And B transpose AB has this form, block diagonal form, where for each one the determinant is minus lambda I squared. So this is, it's determinant is lambda I squared. This is lambda 1 squared, lambda 2 squared, lambda n squared. Okay. So square root determinant A is lambda 1 to lambda n. Alright, so let's prove this lemma. And once we prove this, then we've basically finished because we've reduced to a product of, I mean, this is independent, everything else is 0, so it's a product of blocks. And for each block, we have calculated that the result we get is correct. So we need to show that there's a basis that we'll call E1, E minus 1, E2, E minus 2, En, E minus n, such that well, we have this relation A is of this form. So A, let's say A EK is lambda k E minus k, and A E minus k is minus lambda EK. Right? And then it also means that A squared, applying it twice, A squared E plus minus k is minus lambda squared E plus minus k. Okay, so you see then, so we need to find this basis, but if this is so, then this basis, pair by pair, these are eigenvectors, E plus minus k are eigenvectors of A squared, and in our well, I removed it, but in our assumption was that A squared, so assumption was that A squared has negative non-zero eigenvalues. We see that this is consistent with what we want to obtain. So that means to say E plus E minus are the eigenvectors of A squared that correspond to these negative non-zero eigenvalues. Right? Now, well, so one thing that I've noticed is, so this is a double degenerate, right? So for each lambda k, there is E plus k and E minus k, both are eigenvectors. This was not part of the assumption. The assumption was that A squared has negative non-zero eigenvalues. Right? So let's check that this is true. So if let's say E is eigenvector of A squared with eigenvalue minus lambda squared, then let's define E prime, which is A dot E over lambda. And then we say that A squared E prime is A squared A E over lambda but but here I write this as a times a squared, and then a squared e is minus lambda squared e. So this is minus lambda squared a dot e over lambda, which we call e prime. So you see, then if indeed if e is an eigenvector of a squared with eigenvalue minus lambda squared, then so is e prime. Right? So for every e there's an e prime. And then, well, there remains the possibility that they are the same vector, so we have to check that they are linearly independent. Right? So we do this by reduction ad absurdum. We assume this would be true. So if let's say e prime is some number f times e, right? Then I would write a squared e equal to well, no, just AE, I would write it as, well, first of all, AE would be wait, what would I want to say here? AE is equal to okay, so AE is equal to lambda E prime, but then E prime is FE, so this would be lambda F E on one hand. So this is using this. But on the other hand, I would write well, so applying it twice, I will get that a squared. So I apply once more here, a squared e, and then I apply that AE is lambda, again lambda FE, so this would be lambda squared F squared E on one hand. On the other hand, by the definition of E as an eigenvector of A squared, I would get that A squared E is also equal to minus lambda squared E. And you see the contradiction, right? This is negative, whereas this is positive. So we will obtain a contradiction, right? So that means that our original assumption was wrong. So that means that we cannot have linearly dependent vectors. The vectors have to be linearly independent. E and E prime are linearly independent. Okay? Well, but that's still not enough. We would, for this to be a basis, I would need, well, sorry, not just a basis, but for them to reduce to this form, I would still need for them to be orthogonal. And so let's see this. So E dot E prime is E dot A E over lambda. And but this is antisymmetric, and that so this is multiplying EI, AIJ, EJ, so that's clearly 0, right? Because of antisymmetry of A. So these are also orthogonal. So that is, we've proven the lemma by showing that for every eigenvector of A squared, there are actually 2 independent and orthogonal ones, and using them I can decompose A in this way, right? All right, and then, as I said, once we've proven the lemma, we've basically reduced the calculation of the path integral for A to the calculation of path integral for this case, right? Which we already did. So we can now say that integral dnx, sorry, dnx e x transpose A dot x is now we do a transformation on the basis x, so we can write this as integral dn of bx e x transposed b transposed a bx, right? And then sorry. No, what do I want to say? Oh no, I'm sorry, I want to transform this with B transpose X. Yes, that was the point. So X transposed B. This is X, B transpose X transposed. And then the point is that this result is equal to X transpose A X, because B transpose is 1. Okay? So now we call this thing X prime, X prime, X prime. So we have the path integral over X prime, and this is our diagonalized, so by the Jordan lemma. This is, well, block diagonalized, the way we wrote it over there. And so now we can compute this as products. So let's say product from I is 1 to m to the, well, any one case at each I, right? And since in the n equal 1 case we obtain 2 square root determinant, and the determinant of the full matrix is now product of the determinants of the blocks. This is 2 to the m square root determinant A. So QED theorem. Okay. All right. Now, let's consider also complex integration. By complex integration, I mean that I have a complex conjugate on the left, but I treat the field and the complex conjugate as independent, so I have 2 independent integrations. So xi, yi complex, but without putting yi equal to xi star. This is the same trick as we used in the case of regular commuting numbers, right? Consider the integration over variable and conjugate variable as independent. So, but now again of an n by n antisymmetric matrix A. So what we need to calculate is then e to 1 transpose A over x. And now this is complex integration, so we have to obtain the square of the result of before. Well, except for factors of 2, which will have to do with the form of this action, you know. As I said, in principle there would have been a factor of 2. When we take the same, this and this to be the same, we should have put a factor of 1/2 in here, which would have cancelled this 2 to there. Since we didn't, now we'll get a different result. The result should be just determinant A, which is the square of the what we got there. Okay, so keep in mind this is because we will consider integral deep psi bar, integral psi bar, things like that. So we will have something of this type. All right, so how do we prove this? Well, again, the same thing. The point is, in this exponential, there's arbitrary powers of the exponent, but we have to remember that x squared is 0 and y squared is 0. So because of this, there are no powers greater than 1. But also, integral of 1 is 0, which means, really, that sorry, yeah, I said it wrongly. So there are no powers greater than 1 for x, but what we will obtain now is how should I say this? So this, yeah, let me say it like this. So this is a sum. This is sum of I and j, yi, aij, xj, right? So it's a sum of terms, right? Now, it's true that, so, so if I write a product of these things, of these terms, it's true that there will be terms that contain x squared, but not all of them, right? So here there's only one term that contains, let's say, x1, so one term with x1, and the rest without, right? But here I will have the same thing. So there would be one term with x1, and that certainly will not contribute to when I multiply with this, but there will be others. that will come to pi1 and multiply with x1, right? So in this product, the only thing, so the only contribution but then you also have to think about what contribution is possible. So if there is no x1, then integral dx1 and 1 is 0. So I have to have exactly one of each, right? So I have to have exactly one of x1 and also one y1, one x2, one y2, all of these things. And actually, that means that the integral here will be integral dx1, dxn, dy1, dyn. And now I need to have something with n x's and n y's, right? So there will be a term coming from the nth order, right? Because each order has one x and one y. So the only non-zero term will come from the nth order in the exponent, right? So this is, so the only non-zero term then is what? Well, so 1 over n factorial, that's because of the exponential. And then in this nth order term, I have all the possible products that have only one of each x and only one of each y, right? But in here you see you have sum over ij for each of these, so it's arbitrary I and j multiplied in a. So the way I can write this, I can write this as sum of the permutations p and q. These are permutations of 1 to n, which are, that is to say, p of 1, there's some arbitrary I, right? And here I would write y p of 1, a p of 1, q of 1, and then x q of 1. So that is to say that's one term of the type aij, yi, xj from one of these sums. But then from each I pick a different one, right? Which is, but so the only constraint is that the indices, the indices on y cannot be the same, the indices on x cannot be the same. Which is to say, I have to permute this 1 to n to p of 1, p of n, right? This permutation means I just move 1 to an arbitrary another p of 1 and 2 to an arbitrary p of 2. The only constraint being that it cannot be the same as p of 1 and so on, right? That it's really a permutation of these guys, that the indices don't repeat, right? So then we will have this until y p of n, a p of n, q of n, x q of n, right? So those are the only non-zero terms, right? Okay, but now since this thing is bosonic, it contains two Grassmann numbers, it commutes. So I can rearrange this object such that, in fact, so you see the first one is, in each bracket I have y p of 1, I have y p of some I, right? So the first y's are kind of permuted among each other, but I can unpermute them, right? That is to say, I write this as, I still have sum of p, sum of q, but in each such product, I rearrange the terms such that I always have first y1, then y2, then y3, and so on, right? So in effect, I have this y1, a1, q1, x, q of 1. I mean, it will not be the same q if you want, right? Because here I have p of 1 with q of 1, for instance. If I rearrange, I will have 1, but then some q of something else. But then it's just a redefinition of what q means, right? The point is it's some permutation of the indices. So perhaps let me call it q prime to make it clearer. Q of 1, and then until yn an q of n, x q of n, right? But now once I did this, sum of the permutations p is redundant, so I can just do it trivially. I just write this as n factorial, and then this cancels the n factorial here, right? To be more precise, the way to write this q prime would be p minus 1 times q, right? Because I take a p of 1, q of 1, and I turn it into this a1 q prime of 1. So if I apply p minus 1 both sides, right? Then I get here really 1, and here I get p minus 1 q. Q prime is p minus 1 q. All right. Okay, and now right. So now there's some overall sign epsilon that I will not care about. I mean, independent on permutation. So this overall sign independent of permutation. But then what do I have? So I will rewrite these as, so I will put them in order, y1 to yn and x1 to xn. So I just pull all of these x's and y's outside and arrange them in this order. That's why I said it's an overall sign. So if I would have here y1, x1, and up to yn, xn, then in order to get to this, I would still need to get an overall epsilon. But I don't care about that because that is related to the choice of how do I put the integrals in dnx and dny. And I chose it such to cancel this epsilon, right? But then what I'm left with? Well, then I'm left with sum over q. There's still something. So there's a sign epsilon q that amounts to the fact that there's still a sign difference between this x1, y1 to xn, yn, to yn, xn, and y1, x1 until yn, xn, and y1, xq1 until yn, xqn, right? So that's my epsilon q. And then a1, q1, q of 1 until a n q of n. right? However, this thing here, with this sign of the permutation, this is the sign corresponding to the permutation cube, and this product of matrix elements, this is really the definition of the determinant, right? This is what determinant of A means. That's how you define determinant of A, right? Okay. So now I do the integral dnx dny of this thing. And as I said, the integral is defined such as to cancel not only this, but also the sign. Because, I mean, I choose the order, the sign, the order in the measure, such that I cancel this epsilon when I rewrite it in a form that does the integral. Okay? So that means that in the end, the result is just determinant of A. So the integral is just determinant of A. So we've proven the theorem. Okay? All right. And one check that we need still to do is to check, so this was complex integration, and before we had real integration, so that to check that the two are consistent. So real versus complex integration. And of course, to do so, I can rewrite this complex one in terms of a real one. I write xi is ai plus idi, and yi, now I think of it as really the complex conjugate, in which case is ai minus idi, and then y transpose dot a dot x is really the sum a transpose, I mean this a little a transpose dot a dot little a plus b transpose dot a dot little b. So that's how it should be. But then the Jacobian of the transformation, so dnx dny is written as the Jacobian times dna dnb, right? And then you can calculate this is just 2 to the minus n. So then that works. And again, the determinant of this, so here we get determinant A, but here we get square root determinant A from this term, and then square root determinant A from this term. Right. All right. So we've proven the mathematical tools we want, Gaussian integration. Now let's actually do calculations with that. And as before, we start with our example for everything, which is the harmonic oscillator. In this case, the fermionic harmonic oscillator. And then generalize the field theory. Okay. So, for the fermionic harmonic oscillator, remember, we have this, and then in principle, we could write BB dagger minus B b dagger b minus bb dagger over 2, but then I rewrite this as b dagger b minus 1/2 as opposed to plus 1/2, which was the case for the bosonic one. And as before, so in principle we could follow the path integral in all the ways we did it, but let's go directly to the way that we considered was the best in terms of coherent states. So these were states that were obtained by exponentials of creation operators acting on a vacuum state. Just that now these are fermionic creation operators, and moreover, also betas are Grassmann numbers. So fermionic creation operator, and this is now also a Grassmann number. Like this, so it means that b dagger and beta anti-commute, they don't commute. So in this, because they're fermionic things, b dagger squared is 0. So now I only have the 0th order and the 1st order term in the exponential. The 2nd order and higher are 0 because b dagger squared is 0. But now I can write 1 times beta b dagger 0. These things anti-commute. And now let's see that this is an eigenstate of B. So if I act with this here, so B on the first, B on 0 is 0. And then B dagger is 1, anti-commutator is 1. So when I act with B here, the first term is 0, then this one gives B dagger is B dagger minus B dagger B plus 1. But then B dagger B, well, once I commute past beta, I hit 0, so I get again 0. Now I'm left with just this 1, right? So that means that the result is just beta times 0, right? And then I can write this also as beta times 1 minus. So beta is also a Grassmann number, so beta squared is 0. So I can add for free this thing, B dagger 0. But then this thing is just beta. So this is beta. Okay, so as said, this state is an eigenstate of B with eigenvalue beta. And I also have the completeness relation. One is integral d beta star d beta, beta star minus beta star beta. This is the same as we had in the bosonic case. And then I consider the Hamiltonian with currents. So the Hamiltonian minus then B dagger. So source for B dagger is called eta, and source of B is called eta bar. But in both cases, I put the dagger one on the left and the undagger one on the right. Okay, and then I can just follow through everything that we did for the bosonic case. So we define the transition amplitude for the same thing as in the bosonic case, and also like in the bosonic case, I insert the consistency, the completeness relation, the identity I inserted in between. So I write this with time evolution with Hamiltonians, and then I divide it in an infinite number of steps, and I insert between each step the completeness relation and write it as a path integral. It's exactly the same thing that we did in bosonic case. Nothing changes. And then we get the same thing as before. And then equation of motion is the same. Star minus I omega beta star plus I omega bar is 0. Plus I omega beta minus I beta 0. And solutions again the same. So the details of this I left for you as an exercise. It's really just following step by step what we did in the bosonic case. And then for beta equal beta star equals 0, we get the vacuum functional. The thing that we're interested in. And so finally, we write the vacuum functional. Or partition function that now depends on the sources eta bar and eta as some normalization constant 0.0 times the exponential of minus integral dx omega eta bar of this eta of tau. Okay? Okay, so I wrote all of this explicitly on the board to show to show the steps, but it's really the same derivation. So once I define the coherent state and completeness relation and the Hamiltonian of sources, then everything follows exactly through, like in the bosonic case. So now the only thing that is left to do is to generalize the field theory case. So this was the fermionic harmonic oscillator, but we have to generalize the field theory, which is thought of as an infinite product of harmonic oscillators. And then, so beta we replace by psi and beta star by psi bar. And then integral beta star dot beta becomes integral dt psi bar psi, or minus, taking a partial integration, minus integral psi bar dt psi. And then correspondingly, I have z of eta and eta bar, the partition function, well, some normalization constant, and then path integral. Well, sorry, the first of all, path integral of the exponential of I, then the integral of this thing is replaced by minus integral psi bar dt psi. So integral psi bar dt psi. But then we still had but then we have minus h, and h is omega beta b, which is replaced by psi bar psi. So we have minus omega psi bar psi, and then the source terms. So minus h, that is plus the source terms plus psi bar eta plus eta bar psi. Okay? And then the result of the integration is again a normalization factor that I can call z of 0, 0. And then exponent of minus integral ds d tau. Then I write eta bar s, and let me write here df of s and tau, and eta of tau. So what do we have here? Well, remember omega it should have been I wrote this wrongly, that I knew. How should I have written here? I think I should have put sum of omega or something like this. The point is, or integral, yeah, sum of omega, which means integral d omega over 2 pi, right? And so the point is then the resulting here with this df, what is meant to be? Well, I have these, I have this factor which amounts to a Fourier transform, e to the I omega tau minus s. But I also have the inverse of this object, right? So I define I times the Minkowski action as minus psi bar delta minus 1 psi. That's my definition of the propagator delta, which means that the Feynman propagator that we obtain is minus I, but then times this object that we have here, I times, sorry, yeah, there was I dt, yes, sorry, I dt times, I dt minus omega. Inverse. This thing is understood as an inverse in the space of S and tau, which as before means I take a Fourier transform. This is anyway an integral over omega. So no, sorry. No, what do I mean? Done something. Just a moment, I got myself confused now. Yeah, and here also should be in principle sum of omega. I think that's really the way to think about it. So anyway, the point is that when I invert this operator, what I mean is I write the integral in Fourier space, and then so in Fourier space, I dt acting on this becomes just E. So I dt acting on this gives me I times minus 1, I is 1 times E. So E minus omega. And then the Feynman prescription to avoid the pole amounts to add, as usual, plus I epsilon. And the contour integral now, so in imaginary energy is, so let's say the pole is then at is omega minus I epsilon. So this would be the contour, or another way of saying it, remember could say the contour is like this and the pole is on the real line. And then we can close the contour, let's see, we can close it below. Then if we close it below, then we get a non-zero answer. And that's because in here we have E minus I E. So if S minus tau is negative, no. Seem to have done something wrong. Oh no, sorry, yeah, imaginary part is negative. So if the imaginary part is negative, that means this is minus I times something. Minus I times minus I is negative. So indeed, so if this is positive, then indeed closing in the lower half plane, I get an exponentially decaying object. So this integral is 0. That means that the integral itself is non-zero, first of all, only if S minus tau is positive. If S minus tau is negative, I have to close in the upper half plane where there are no poles. So I get a theta of S minus tau. So the result is non-zero only if S minus tau is positive. And then, well, this is already a pole, so the residue is just comes from the exponential on the top. So this is E minus I omega, then replace E by omega, S minus tau. Okay. Okay, so for a single omega, the result for the Feynman propagator is just theta S minus tau, E minus I omega S minus tau. And now further, let's consider the Euclidean case. As before, I write that the time in Minkowski is minus I times the Euclidean time. And then the Euclidean path integral. So is given just by replacing in here. So integral deep psi bar deep psi exponent and so here I also have integral dt. So note note that I have I integral dt, and then I have psi bar, and then I have I dt over minus times 1 over I d over I dt minus omega psi, right? And then I dt Minkowski is equal to I dt Minkowski is equal to dt Euclidean, and then this is also dt Euclidean. But I have the overall minus, so this is minus integral dt Euclidean of psi bar dt Euclidean plus omega psi, right? So here we get minus integral dt Euclidean psi bar dt Euclidean plus omega psi. Then the other term is just I dt Minkowski, which is minus I dt Minkowski is dt Euclidean times this plus integral dt Euclidean psi bar eta plus eta bar psi. Okay. So that's my definition. And then in the result, I get normalization factor. And then we have minus these things, but each comes with a minus I, so and then minus I squared is minus 1. Right? So that cancels the minus in front. So so I get integral exponent integral d tau, let's say Euclidean, ds Euclidean, eta bar s Euclidean, and then the propagator d of s Euclidean, tau Euclidean, eta of tau Euclidean, right? And then d of s Euclidean, tau Euclidean is understood as the inverse of this propagator. So in here, remember, in the exponent, what we get here we call the Euclidean action. So the thing that I'm inverting is the dt plus omega, the Euclidean plus omega inverted in S Euclidean, tau Euclidean. That is to say, I take the Fourier transform over energy, minus I e minus tau of this propagator, and in it dTe acting on this gives minus I wait, something is not, yeah, minus I, so minus I energy plus omega, and now I write this as an I upstairs, so I'm multiplying both sides with I, and then I times minus I is 1. Okay? Perhaps I should have written this Euclidean as well. And the rotation to Minkowski space is also the same. Is the same logic as before. So integrating over E Euclidean amounts in E integrating over the imaginary line, but then I want to rotate by pi over 2 minus epsilon as before in order to get to the Feynman propagator. And then once we do that, we obtain the rotated case. And we obtain that D of I S Euclidean I tau Euclidean, which is S Minkowski tau Minkowski. Sorry, the other way around, right? Yeah, so TE is I times Minkowski. So I write in terms of, I write S Euclidean as I as Minkowski and I tau Minkowski. So I rewrite I rotate the integration, and I rewrite this as integral E Minkowski over 2 pi. Here obtain E minus omega plus I epsilon prime minus E Minkowski, S Minkowski minus tau Minkowski, which is just the Feynman propagator. So the same logic applies. All right. And now finally, as we saw the Lagrangian in Minkowski was minus psi bar d slash plus m psi. So if I go from quantum mechanics to quantum field theory, then dt becomes d slash, right? Or I dt, I should say, becomes d slash. So the fermionic Lagrangian in Minkowski is this one. And then, as before, the Minkowski, the fermionic Lagrangian in Euclidean becomes with just a plus sign, as we saw in the Euclidean action. I took out the minus sign, and then we're left with psi bar psi with the same operator in the middle. So this is plus psi bar d slash plus m psi. Okay. So the point is, when you do this Zeek rotation as before, we write I times the Minkowski action as minus the Euclidean action. And as we saw before, well, this constant term just changes sign. And then the same thing happens for the d slash corresponding to IDT. But there's one thing that must be noticed. So you notice the I here, so there was an IDT that became d slash, and that was changed. And that should tell you something. In fact, because this was gamma 0 d0 plus gamma IDI, right? Gamma IDI remains invariant, so that's fine. But gamma 0 d0 behaves like IDT. Right? This is dt. Right? And the point is, so this was changed to dt Euclidean, and here this is changed to gamma 4 d4. Right? So we note something, that gamma 4 also changes. So gamma 0 changes to gamma 4. And the reason is because we have, in the Clifford algebra, we have that the anticommutator of gammas is given by the metric. So the metric in the 0, 0 directions changes sign, right? So gamma 0 squared is -1 in this case, right? But on the other hand, gamma 4 squared is +1, right? Because we're going from Minkowski to Euclidean. So that means that I need to take also gamma 4 to be I gamma 0, which is the same rotation as for time, as time Euclidean is equal to I time Minkowski. Right? So then there's one more thing to do. So you notice that I called psi bar the same thing, but I had in the back of my mind that psi and psi bar are different variables integrated separately. But then if I remember that psi bar is actually the conjugate of psi, I have to keep the definition while changing gammas. So that means that I have to define that psi bar, which is equal to psi dagger I gamma 0. I have to define this as psi dagger gamma 4. Whatever, it doesn't matter if it's up or down. Right? So I gamma 0 is equal to gamma 4. And I want the definition to remain, so I have to define it like this. Yeah, and one more thing. So in Euclidean space, with this definition, now all of the gammas are Hermitian. So before we had that the spatial gammas were Hermitian, then the temporal gamma was anti-Hermitian, but now they're all Hermitian. And of course, that, well, it's Euclidean space, so up and down is the same gammas. All right. So the free partition function then, which is just, as we said, the sum of harmonic oscillators, the sum over omegas, if you want. Deep psi, exponent minus integral d4x psi bar d slash plus n of psi. That's the free action for the fermion. And then the source piece. That was the definition, and then this becomes eta bar d slash plus n inverse eta, right? So, whereas before this propagator is written by writing minus s Euclidean action as minus psi bar delta minus 1 psi. The thing that is in an exponent, I write it as minus variables with the inverse propagator in the middle. Just that now I will call this, well, this is a little bit confusing, so maybe let me say like this, but delta is now called SF, as in fermionic propagation. That's the standard notation. So then SF of x and y is d slash plus n inverse, which means as before, Fourier transform of this thing. So d slash is d mu gamma mu, and d mu acting on this gives ip mu. So this is ip mu gamma mu, or in other words, ip slash plus n. But then I do the same thing as before. I multiply and divide by I. So I here and I here, and I times 1 sine is 1. Okay? Right. So this thing really means that this is a Green's function, right? So d slash plus m on SF should give me a delta function. So d slash plus m on SF integral d4p 2 pi 4. Then inside, so here I have e to the I p x minus y, right? And then on this one, d slash plus m gives I p slash plus m. And then here I had I over p slash plus im, or 1 over I p slash plus m. So indeed, this is the Fourier transform of 1, that is the delta function. Right. Oh, sorry. Here I had the minus, right? It's 1 over ip slash plus m, and then I multiply by I, both up and down. I get minus p slash. Another form of writing this. So I said that this is 1 over ip slash plus m, and then I rewrote it as 1 over minus p slash plus m, I over minus p slash plus im. But another form is to remember what we said, that ip slash plus m, ip slash minus m is minus p squared minus m squared. Right? We said this, well, we did it in x space, but the same is true in momentum space, that the product of two Dirac operators is equal to Klein-Gordon operator. The product of two Dirac operators with different masses is equal to Klein-Gordon operator. So this is equal to minus p squared minus m squared. In other words, I can rewrite this as 1 over ip slash plus m as minus ip slash plus m over p squared plus m squared. Yeah. No, there's a minus sign wrong here.
The I was in the mass, right? The master, not in the Peter, is you. Oh, sorry.
No.
There is an extra I.
No, but I seem to have a different sign with respect to my notes. Let's see, what do I? So I wrote 1 over minus p slash plus im. That is minus I times this thing. Minus I gives, oh no, it gives right, it's right, sorry. No, it's it's consistent, yeah. Okay. Then consider also a general endpoint function. General n plus n point function with size and psi bars will be, as before, written as a class integral, d psi bar d psi into I times the fermionic action, but with the same insertion, right? So what I mean is not just the propagator, but any endpoint function will become path integral as before. There's no difference. In particular, for the propagator, we go back to this thing. So this would be t psi of x, psi bar of y, and this is this thing. d4p 2pi4 I px minus y minus pi over 1 psi p slash minus n plus ix. And yeah, so all of the other things are the same way. And for the Wick theorem, again, things are in the same way. The only thing I have to take care of when I talk about the Wick theorem is to have the right sign for the right order and right sign for the fermions, because now fermions anticommute. So if I have a path integral with both fermions and bosons, fermionic sources and bosonic source, I write E minus S interaction of so I should write dD eta dD eta bar. So where did I write this? The path integral with the source, yeah, here. So you see in the exponent I have eta bar on the left hand, but eta on the right. So only if it's on the left, I can act directly with the derivative and get a plus sign. If it's on the right, I have to go past a fermion, so I get a minus sign. So I have to write minus dD eta and dD eta bar and dDj, acting on the free eta bar eta piece and the bosonic free part. Okay? And Kohlmann's lemma is also obtained in the same way with the same thing. The only difference is the minus sign taking care to act only on the left on fermions. So Kohlmann's lemma, I have to write that f of minus dD eta bar z is z minus dd psi bar and f psi bar psi e to the psi eta plus eta psi bar eta plus eta bar psi at psi equal to psi bar equals 0. And then applying it to the Wick theorem, I get the second form. Second form for Wick. Again, the same thing. So the only thing I have to take care of is when I act with dd psi or dd eta, I put a minus sign because I have to flip past the bar field. So z of eta by eta and j also minus si is also minus dd psi dd psi sf dd psi bar minus si psi bar psi ddj plus integral psi bar eta plus eta bar psi times z 0 of j psi equal to psi bar equal to 5 equal to 0. Okay, so it's really the same thing. All right. So really everything we do with fermions in the end, once we remember that the propagator is different, the only thing that's new is we have to take care of minus signs. Right? You have to remember that in order to get the plus sign, I have to act with derivatives only on the left, directly on the fermions. If I have to hop past the fermion, I need to get a minus sign. So let's write down Yukawa interaction Feynman rules. So the Yukawa interaction is the interaction between a fermion and a boson. And it's the simplest interaction you can have. So as we saw, you cannot have a fermion by itself. That's not Lorentz invariant. Psi by psi, however, is Lorentz invariant. And so once you have this to interact with a boson, the simplest thing is to multiply with a scalar. Right? That's the simplest interaction you can have. That's called the Yukawa interaction. And I will put a coupling G for it. Okay? So in this case, I write the second form of the Kalman lemma. So I have to act of the Wick theorem. So I have this free part where I replace I replace the order. So delta with minus 1 with delta and phi with dd phi. And then the same thing for the fermions, just with taking care of the sign. So minus dd psi sf dd psi bar. And then acting on E minus G integral E for x psi bar psi phi, which is the interacting part. Right? This is the term that comes from E minus S interaction. And then I write also the free Sorry, I also write the source term, and in this part I had not obtained I had not written the free, I had not written the second form for the bosons, but now I write the second form for the bosons as well, meaning that I have this part acting on the interaction of the bosons, and so there's nothing left on this side. There's no free partition function to act on. It's just the interacting piece and then the source term. So plus integral before x psi bar eta plus eta bar psi plus j phi. Then put psi bar phi. Okay? So this is the partition function. And then, for instance, if I want to check the free two-point functions, two-point function for fermion, that is the propagator. So let's check that we get it. So psi of x, psi bar of y, 0 is obtained as derivative with respect to eta bar, then minus derivative with respect to eta on the two-point function, on the partition function at source is equal to 0. So in this case, since I take one derivative with respect to eta, one with respect to eta bar, I'm only interested in the term linear in eta and eta bar. That is to say, I am interested in the term with no interactions. So this term will not contribute. And in here, I will take, so also this term is not of interest to me. So I will take derivative with respect to psi and psi bar, acting only on these things. Right? So I take one derivative acting on this, and then from this I get two terms, and then correspondingly I will get so I'll get from here I will obtain minus, and then dd psi will give me, sorry, minus dd psi will give me eta bar, so plus eta bar, then sf, and dd psi bar will give me eta, right? And then acting with dd eta bar will kill this, with minus d eta will kill this, and I will get finally sf of x and y. All right? So we've checked that at least the free two-point function works with this formula. Now, if I want to write Feynman rules, I want to write a line between x and y for this free propagator. But note something, that these are fermions, so when I interchange them, I get a minus sign. So I have to put an arrow on the propagator. So from x to y. Right, from the first one to the second one. because if I interchange them, I will get a minus sign. Okay. Then, well, this interaction, it's the interaction of any three fields. If these would be scalar fields, I would write a coupling of minus G, right? Now the only thing is that these are fermions. So I have to remember, well, these fermions come with a direction, as we saw, which is related to the fact that their ends don't commute. So I have to write something like this for the fermionic line. And then to distinguish it, I'll write some other kind of line, let's say a dotted line or something, for the boson. So this is the Feynman rule for the vertex. Okay, so we have a Feynman rule for the propagator, for the vertex. What else? I mean, for bosons we wouldn't have anything else. But for fermions we do have something because we have these pesky minus signs. Oh, I should say, so remember these are psi bar, psi, and phi, so they're all three different kind of fields. That's why I have a minus G with any factors of any kind in front. Then, so the interchange of fermions is the interchange of fermions gives some interesting minus signs. So we see that in this formula we have this exponent minus d deep psi SF d deep psi bar, and we act with it on factors of so if I have interactions, I will act with it of factors of psi bar psi. So if I act on psi bar, I get SF. That's how I define it. But I will act on psi bar psi phi for the vertices. So I will act with products of these things on things like this. And now let's notice what happens if I have a diagram that contains a loop. Of fermions. Okay? So if it contains a loop of fermions, then each of these things are of this type, psi bar, psi, phi. So each of these things comes with psi bar, psi. But then I have, so let's say I have, well, 1 to n. Then I will get SF x1 minus x2, SF x2 minus x1, next x3 until SF, let's say xn minus x1. Okay, that's my loop. But then what kind of sign do I have? Well, yeah, actually, I should have written it like this. SF xn minus x1. That was actually the point. So in order to write it like this, I have to take this last xn, this last psi, and jump over the whole other things. But these are pairs. There's 2 and so on. And then there's 1. So all of these things, there are 2n plus 1. So when I jump the last psi, in order to put it here first, to get the argument, the first argument is the first derivative. So in order to put it first, the last psi has to jump over all of them, which means that I get an overall minus sign. Okay? So that means that for every fermion loop there's a minus sign. So that's the only new thing, right? Fermion loops comes with minus signs. So then the rules are, of course, scalar propagator is as before 1p squared plus m squared. Fermion propagator is this 1 over I p slash plus m, or in other words, I over minus p slash plus I m, or yet in other words, minus I p slash plus m over p squared plus m squared. These are 3 forms of the scalar propagator. And of course, these are nice and compact, but this is the one that you would actually lose because this is formal. I mean, remember p slash is p mu gamma mu, it's a matrix, so it means inverting a matrix. So it's easier to write it this way because here you don't have to invert anything, just have a matrix. Then the vertex psi bar psi phi is minus g, and there's a minus sign for the fermion loop. So these are the relevant Feynman rules for the Yakava interaction. So just let's say this would be the scalar, and then this is a fermion, and this is a vertex. What else? And in Minkowski space, of course, so I have 1 over, so minus I over p squared plus m squared minus I epsilon for the scalar propagator. For the fermion, I have minus I times this thing, times, let's say, minus I p slash plus m over p squared plus m squared, which now gets the same Feynman prescription as the scalar propagator for p squared plus m squared minus I epsilon. And, vertex minus ig, and minus 1 for fermion loop. Right? So these are all the way you expect them. Right? So the going from Euclidean to Minkowski is the same thing. The only new thing really for the Feynman rules is the presence of this minus sign for the fermion loop. Otherwise, you could have guessed everything else. And one more thing to say, which is that I said what happens only for the Yukawa interaction, but in principle I could write some more general interaction between fermions and bosons, or fermions and scalars. So general fermion scalar interaction. Let's say maybe there are several scalars and so on. And so the only new thing is how to write the vertex. Remember, I wrote for you a formula for the vertex in the case of the more general bosonic theory. And now I say the same thing when I have also some fermions. So, of course, we have to consider a Fourier transform. So let's say Px plus P prime y plus Q1z plus Qn Zn. Right? In order to get the momentum version for this. But then dd phi 1z1, dd phi mzn. That's the same thing as we had before. And now the only thing that happens is this minus sign for the fermionic piece. And then this one acting on minus si as before. Psi bar, psi, phi 1, phi m. Okay? So that's the only thing. So really, again, you could have guessed it, the only new thing is the presence of the minus sign for the fermions. All right, so that's everything I wanted to tell you today. Do you have questions? Oh, well, okay then. So I'll see you on Monday.